So the TCP Connect full open scan, all right, so the TCP Connect, we have the handshake here, right? It's a full connection, it's an open scan. You're blatantly advertising that I'm connecting to you. TCP Connect scan detects when a port is open by completing the three-way handshake. So you send a SYN, they send a SYN plus an ACK, and then you send an ACK back, and that completes the three-way handshake. So the TCP Connect scan establishes a full connection and tears it down by sending a reset packet. It does not require super user privileges. This is just anybody from the wide open can connect. So let's take a look at it down here. Scan result when a port is open. So scan result when a port is open. You will see test questions about this. So you send a SYN, you get a SYN plus an ACK back, you send an ACK, and you send a reset. So that's what it kind of looks like when you get an open port, okay? And then if you have a closed port, you send a SYN and you get a reset back. So if you get a reset, then you know the port is closed. A stealth scan or half open scan. So one more thing, some of these ports will behave differently between Linux and Windows. So just know that this is the Windows version, okay, for the test. If they don't specify, just assume it's Windows. Stealth scan or a half open scan. All right, so let's take a look at this. Stealth scan or a half open scan. So a half open scan is when you just send the SYN, right? So let's take a look at the picture on the right. The port is open. You send a SYN, you get a SYN plus an ACK back, so there's two flags set, and then you send a reset. So that port is open. And if you send a SYN, you get a reset back. So you know that it's closed. That's a stealth scan. So inverse TCP flag scanning. Attackers send TCP probes with a TCP flag set, fin, urge, and push. We know that's a Christmas scan set, or with no flag set. So it's a null scan. So it's either Christmas or null, right? Those are opposites, inverse. No response means the port is open, and a reset means the port is closed. So if we take a look at the port is open example, probe packet, we send a fin, urge, and push, or a null, and then we get no response, the port is open. If we send that same thing, the fin, urge, push, which is a Christmas scan, or a null, then we get a reset ACK, then the port is closed. A Christmas scan. In a Christmas, attackers send a TCP frame to a remote device with the fin, urge, and push flag set. That's a Christmas scan. We light it up like a Christmas tree. Fin, urge, push. Fin scan works only with OSs with RFC 793 base. So there's going to be some variation depending on what standard they're adhering to, okay? So it will not work against the current version of Microsoft Windows. So it works on older systems, and you get some intrinsic differences between Linux and Windows. So let's just take for granted on the test that they're talking about Windows unless they specify otherwise, and again, it will be an older version. They've fixed all this stuff. This is all old stuff, right? So if the port is open, fin, urge, push, you get no response. If the port's closed, we send a fin, urge, push, we get a reset. So reset means the port is closed. ACK flag probe scanning. So attackers send a TCP probe packet with the ACK flag set to a remote device and then analyze the header information, the TTL and window field, that's the header information, of received reset packets to find whether the port is open or closed. So the TTL-based ACK flag probe scanning, ACK probe, and you get a reset. So if you get an ACK and a reset, that's the scan. So the Windows-based ACK flag probe scanning, you send an ACK and you get a reset back. So if the TTL value, over on the left here, if the TTL value of the reset on the particular port is less than the boundary value of 64, then the port is open. If the window value of the reset packet on the particular port has a non-zero value, then that port is open. Okay? So that's the difference here. ACK flag probe scanning is kind of a newer thing. ACK flag probe scanning continued. ACK flag probe scanning can also be used to check the filtering system of a target. Attackers send an ACK probe packet with random sequence numbers. No response means the port is filtered, so they're using a firewall, and a reset response means the port is not filtered. So here's an example of it. So the idle or the IPID scan or the idle scan. All right, so that's what we're going to talk about now. Most network servers listen on TCP ports such as web servers on port 80 and mail servers on port 25. So the SMTP is 25, not checking your mail, but transferring mail, right? And that port is considered open if an application is listening on the port. One way to determine whether the port is open is to send a SYN, or a session establishment. We talked about that SYN. We get a SYN plus an ACK back, and then we send an ACK packet to the port. So the target machine will send back a SYN or an ACK session request acknowledgement. Not an ACK. It'll send a SYN plus an ACK, right? Not an OR there. And then if the port is open, and a reset packet if the port is closed. So we get nothing if the port is open, or no, we get the SYN ACK if the port is open and a reset if the port is closed. So if you send a SYN, you should either get a SYN ACK or a reset back. A machine that receives an unsolicited SYN ACK packet will respond with a reset, and unsolicited reset will be ignored. Every IP packet on the internet has a fragment identification number, or an IPID. So that's the fragment identification number. The operating system implements the IPID for each of the packets sent, increments. It increments the IPID for each packet sent, thus probing an IPID gives the attacker a number of packets sent before the last probe. So it used to be just a sequential set of numbers. Now they kind of randomize it wherever it starts. So it might start, back in the day it used to start at, let's just say 1. And then after some number of hours or days, you're up to 10,000, 10,001, 10,002. It may skip one. Different implementations had different logic there. But nowadays, when the attacks came where people were predicting these sequence numbers on idle machines for idle scans, it got changed. So what happens is they randomize where the communication starts. So communication may start at 5, it may start at 5 million. So then it will increment there, but it'll increment at random bursts. So it might go from 1, it might increment from 1 this time, it might increment to 5 next time. So every time you send a packet, it doesn't increment sequentially. It might jump from 1, 5, 30, 40, 60 to 12, that kind of thing.